Hello everyone, it's Mr. Waz. Welcome to WasleyScience. Today we're going to be discussing plate tectonics. So we're going to discuss how the theory of plate tectonics came to be. Then we will discuss what plate tectonics contribute to. And last we're going to talk about the science behind how the plates on this Earth move. So let's get started. So we're going to start by talking about a man named Alfred Wegener. Now, I may have you do this in class, and if I don't have the time, I'd like you to do this right now. So I'd like you to watch the video on the bottom right over here. You can go ahead and click on that now. But I'd like you to answer these 4 questions while you listen to the video. So I want you to write down who is he and what kind of scientist was he, because that's really a big important part in this story. What was the name of his theory? And write down 2 things that he was right about in terms of plate tectonics and 2 things that he was wrong about. So you can go ahead and get started on that. He's a very interesting guy. Now that you've learned about Alfred Wegener and all of his evidence to show plate tectonics, let's start to talk about them and break them down here. So the first piece was something that was pointed out years before him, and it was that the continents kind of fit together like a puzzle. And the easiest one to see is South America and Africa, but you can really start putting them together as Wegener did when he put them all together into the one big supercontinent we call Pangaea. The next piece of evidence was that fossils of plants and animals exist on different continents. And that was really strange for a lot of people, and at first they thought they were land bridges and all these sort of crazy things that didn't really make sense. So yeah, there were animals that were on one end of a continent and then on the other, and this sort of sense of how the continents fit together. So that was another piece that supported this idea of Pangaea. The third thing was that mountain ranges on one continent match with mountain ranges on another continent. And again, Africa and South America. So the west coast of Africa fits, the mountain ranges that is, fits quite well with the east coast of South America. So again, it just keeps supporting this sort of idea that these plates actually move and that they were together. And the fourth piece is that there is evidence of similar climates at the same time in areas that are not currently close to each other. So that's a little confusing. So what that's saying is Antarctica, which is very cold right now, of course, and it has really not moved over the past millions and millions of years. It's kind of just stayed where it was. But at one point, Africa and South America, India and Australia, they were all connected to Antarctica on the most southern part of the southern hemisphere. So what this is saying is that those areas there were once very, very cold, and there is evidence that supports that through the type of rocks and sediments that they have and what sort of animals that were there as well. If you dig deep into the bottom of Africa, you can see that there was once glaciation there, and there can't be any glaciation right now where Africa is because it's just too hot. So this shows that the bottom of these plates were all really cold at one point. So that was just another piece of evidence, and all these things added up to the idea that these plates move around the Earth over millions of years. So Wegener had a lot of reasons to show that the plates move around. But when it came down to why and how they move around, he had no idea. And unfortunately, he did die. He was from the Arctic doing an exhibition, and he fell through the ice and was frozen to death. Very unfortunate. But then this guy, Henry Hess, he kind of filled in the missing puzzle pieces here. So he was a captain in the U.S. Navy, so he was on a ship, and he had this new technology called sonar. And what this did was it sent a sound to the bottom of the ocean, and then the sound would come back to him at some sort of time, and he could change that time into distance and figure out how deep the ocean was. And it was meant to locate submarines that were in the water. But he decided to just leave the thing on while he was cruising around the Atlantic Ocean. and he found something very, very interesting. He discovered and developed the theory of seafloor spreading. So if you take a look at this diagram in the bottom left here, he didn't do all of this, of course, but he figured out that the Atlantic Ocean in the middle of it has this huge trench. All of a sudden it gets very, very deep, and that there are these mountains as well in the middle of the ocean. They just thought that the ocean was just flat the whole time, but he found these canyons and these trenches and all these things, and he realized that this is where the plates are actually forming. So what I want you to do here is, after I remove this big old text box in the middle of the screen, I want you to press pause on this video and stare at these three maps and find the pattern. So what I wanted you to see is that the locations of where we have earthquakes, where there are currently volcanoes, and where the ocean dramatically changes its depths are like in the same area. Look at the top diagram here. You can see all these black dots represent earthquakes, so you can really see where the plate tectonics are. You can see where they are. They're not just at the end of Africa, they go all the way to the middle of the Atlantic Ocean. So you can see them all around here where I'm moving my mouse. And then you can look at where there are volcanoes, and you can see here that they are like in the same spot that where we see earthquakes. And then you can look at the ocean depths here, and you can see that they are where we see earthquakes and volcanoes. So we took all that and we said, wow, yeah, there's a lot of action going on these parts of the earth. That must be where the plates are spreading from each other and colliding with each other. And that causes a lot of friction, and that causes earthquakes to occur and volcanoes to rise. The theory of plate tectonics explains three things that we have. It explains why we have mountains, because that's where two plates are crashing into each other at convergent boundaries, and that's where mountains are forming. They explain earthquakes, which is the friction of two plates colliding with each other or subducting underneath each other, which causes the plates to shake and move. And then it explains volcanoes. And that is a effect that occurs when there are subduction zones, and we're going to talk about later why we have volcanoes where we have them. I know that we have talked about the layers of the earth previously this year, but we need to review and then elaborate off of it. So let's start from the middle of the earth. We have the inner core, which is made of iron and nickel, and it is solid. And then around the inner core is the outer core, and the outer core is liquid. It's extremely, extremely hot. That's really a key thing here when we talk about the plate tectonics, and you will see why. And then we have the mantle, and something we did not do before with the mantle is we did not break down the mantle into its different parts. Most of the earth is mantle. The top of the mantle, where that sits directly underneath from the Earth's crust, and you can think of a name of the Earth's crust called the lithosphere. That's what we call the Earth's crust. That layer that the mantle is at sits on top underneath the Earth's crust is called the asthenosphere. So what that is just this kind of, it's kind of like this rigid plasticky mantle material that the crust rides on top of. And kind of think of it like a conveyor belt, like on a treadmill. That's what this layer is. It sort of rides along with the crust as these plates are crashing into each other and subducting underneath each other and splitting apart. That's what the asthenosphere is. And then the other parts of the mantle are less solid-like and more closer to liquid-like. And as you get closer and closer to that liquid inner core, it becomes less solid and more liquid until finally it's just all liquid in that outer core. What I'd like you to do now is I'm going to give you guys some terms, and I want you to use the internet to find the definitions to these words. So we have mantle, mid-ocean ridge, seafloor spreading, the subduction zones, the lithosphere, the asthenosphere, and last, convection. And I know that word kind of seems out of left field, but you will see what I mean. I want you to go back to your heat transfer unit and look up what convection is. Alright, there are three types of plate boundaries. The first one that you see at point A here is called the divergent boundary. So this is the part of the plate that is spreading apart from one another. And you can see by the arrows that's what's going on there. And take a look at this symbol right here, because you will see on plate boundary maps that when you see two arrows that are leaving one another, that would signify a divergent boundary. So usually these exist in the middle of oceans, but when they are very young divergent boundaries, they can be seen on land. Eventually what happens is the ground it starts to bubble up and then caves, and then water gathers in that area, which becomes an ocean. For our second boundary here, we have a convergent boundary. So there's different types of convergent boundaries. You can have a continent-continent convergent boundary in which land is hidden land, and then you can get some serious mountains going. You can have a situation like in this one here, where an ocean part of a plate is crashing into a land part of plate or continent part of plate. So we have what this is called is a subduction zone. So the ocean plate, since it's heavier, is sinking below the continental plate. And then you can also have a situation when an ocean part of a plate hits an ocean part, and one ocean just sinks under another. And that happens in the middle of the Pacific Ocean and some other places on Earth. Our last type of boundary is a transform boundary. So this is when two plates, rather than crashing into each other or spreading apart from another, they just slide by each other, and a lot of friction goes on there. So take a look at the symbol here, because when you guys do your geological analysis report, you will see a lot of those. A lot of you guys have some transform boundaries. So that's really important. One example of a transform boundary is the San Andreas Fault in California. So this is a nice colorful diagram that shows the different names of the plates that we have on Earth. We can see that we sit on the North American plate, and down here is a little tiny plate called the Caribbean plate. And we also have the Australian plate and then the Antarctic plate. It looks like it's huge, but the way that the map is designed, it's actually not a very large plate. And we have the Eurasian plate, which starts here and then ends up on the other side of the map. But what's cool here is that you guys can see where there is a divergent boundary, which is like right here, and then when there is a transform boundary, which is right here, and then you can see where the convergent boundaries are. So right here, 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 and then in several other places on this map. So this is a nice colorful map that shows the different boundaries between all the plates on Earth. Now we are at the part of plate tectonics when we talk about how these massive plates move. So with step one, what's interesting about step one is it's still debated to this day what the initial driving force of these plates are. It was developed in the 50s and 60s, and we're still not 100% sure with how it all started. But what we do know is that the inner core of the Earth has, the inner and outer core of the Earth have a massive amount of heat. And this thermal energy is basically infinite. And it is heating the mantle layer. So the reason the mantle layer is hot is because of the heat from the inner and outer core. That's essential. So as the mantle is being heated, by the outer core, because that's what the mantle is in contact with, is the liquid outer core. This magma is heated up and it rises straight to the top of the mantle, to the asthenosphere, because it is less dense. And as we know from Unit 2, with how convection works, things become heated and then the heat rises. And these areas of the lithosphere crust become thinned out from the heat that is in the mantle. And as that becomes thinned out, it begins to split the crust apart. And when the crust begins to get split apart and that heat is able to rise through the lithosphere, the plates begin to move. And what's really essential here is take a look at where my mouse is as the heat is coming up. So this mantle is being heated. It comes out through the lithosphere, but most of it, a majority of it, actually rides along the bottom of the lithosphere. And that's what this sort of asthenosphere becomes, is this upwelling and riding along the bottom of the lithosphere. Here's what's interesting about step 3. As the mantle is, the asthenosphere is moving this lithosphere plates apart from one another, the farther you get away from the mid-oceanic ridge, the older, thicker, and more dense the plate becomes. In other words, this area here, where my mouse is very young, it's very thin, and it's not very dense. But on the other side of the plate, it's the oldest, it's the thickest, and it's more dense. And it's a very easy to tell sort of thing that these plates become older and thicker and more dense as they move away from the ridge, which makes perfect sense because this is where the plate is being born. You got to remember that the oceanic crust is actually just mantle coming up into the lithosphere. So the lithosphere is really just hardened mantle. And the farther away you get from the ridge, the more longer time ago that part of the lithosphere was formed. The subduction zone, you got the oldest, densest, and most thick part of this crust. And what happens is it's so old, it's so thick, it's so dense that it wants to subduct below the other part of the lithosphere, the other part of the lithosphere that is converging with it. So it ends up sinking and forming a deep trench. Alright, and step 4 is when things start to get a little crazy, so make sure you are listening very closely. As I was saying before, that part of the crust is very old and dense and thick, and it's sinking below the other plate. And what it does is as it begins to sink and fall, it starts to drag the rest of the plate with it. This is called slab pull. So the force of slab pull is due to gravity. This oldest and thickest and most dense part of the plate is literally fallen into the mantle. It's subducting into the mantle. The rest of the plate is getting pulled down with it. The example I always used in this situation was, imagine that you were trying to save your friend from falling off a cliff, and they were hanging off a cliff and you were holding on to them. They would be like that part of the plate that was pulling you down. So the force of gravity would want to pull you down off the cliff with your friend. So that is like what slab pull is, but with plates. And now what's really interesting is what they are beginning to start to support is that slab pull is the real driver of the movement of plate tectonics. So it's not necessarily where the plates are forming that's driving them to be moved. It's really on the other side over here in the subduction zone, that because the plates are being pulled down into the mantle, new plate is ended up being forced to be created on the other side. So in other words, it's not that the plate is pushing forward, it's that it's being pulled down. And as a result of the plate being pulled down, new plate has to form on the other side in the mid-ocean ridge. So that's something that they are discussing now in universities. I just think that's really interesting. Here's my favorite part of the movement of plates. As that plate is subducted into the mantle, it gets a little revenge. It starts to cause some resistance as it's going into the mantle. Remember, that mantle is not just liquid, it's very plasticky, rigid stuff. So it's crashing into the mantle right here. You can see the heat that's forming. It's just like if you rub your hands together, you start to get friction. That's what the plate is doing as it's crashing into the mantle. So all that resistance causes massive, massive amount of heat. And that heat begins to rise, because as we discussed in Unit 2, heat rises. And when the heat rises, it starts to form volcanoes above in the lithosphere, and volcanoes begin to form. It also forms earthquakes and even tsunamis. It's not really here where you see tons of volcanoes and earthquakes, but it's actually a little ahead of the plate, because underneath us, where we can't see, that part of the plate that has subducted into the mantle is crashing into the mantle, and it's causing resistance and heat to rise and form volcanoes and all that kind of stuff. And it's going to keep going down and down until it finally reaches the outer core. And when that plate hits the outer core, that's when it's really going to melt and break off. And once it breaks off, at that point there was plenty more that was subducted into the mantle. And then it just repeats the pattern. It just repeats this sort of cycle process. And that's how plates move, and that's how they've been moving for millions and millions of years. What you can do now is use this diagram to review what we have been talking about. It may be helpful for you to look at number 1, and on your notebook make a number 1 and write down a description of what that is and what it's doing, and then go from 1 to 2 to 3 to 4 to 5, 6, and finally 14. And you should be able to describe short and briefly what that is showing. And here is a much simplified diagram that explains the movement of plates. The next slides that you're about to see show what the Earth looked like 237 million years ago to present. And then we're actually going to look at what we are predicting the Earth is going to look 250 million years from now. We can see that 237 million years ago, that's when we really had Pangea going on. And we had this huge ocean over here. Then we can see things beginning to break apart. North America begins to break apart from Pangea. And then we can start to sort of see South America and Africa forming, but Eurasia is still not what we recognize today. And one thing really cool is check out that huge river that ran across North America. Pretty crazy. And we can see that Australia is still hanging out with Antarctica still, just won't let go. So Australia is starting to break away from Antarctica. That river that we saw in North America is really no longer there. Now there's just kind of like this huge bay or something. And Europe and Asia is starting to form its own sort of thing. 50 million years ago, we can see that Asia and Europe are starting to form a little better. North America looks a lot like what we see today, and Australia is now finally its own continent from Antarctica. Now the Himalaya mountains have really formed on the India plate, and North America looks like it did today, as well as South America and Africa, and Australia has moved quite north, and the Europe and Asia plate have collided into each other. 18,000 years ago, it was very cold, and that was our last ice age. and we can see that there was so much more land. Like, look at Australia, for example. Look at Antarctica. See where it's kind of light blue? That was all land. Yeah. So there's a lot more land when there is ice ages. And then we are at what we see today. So this is modern world. The future, so this is 50 million years from now. So now it's kind of getting really interesting here. We can see Antarctica starting to move with the South American plate. We're moving away from Africa and Europe. And we can see here that there's these serious Mediterranean mountains that form. And Alaska is colliding into Russia. And we can see now that in 150 million years, all of a sudden, they're going to start to, Alaska and Russia are going to start sort of leaving away from each other, and we're going to start to form back with each other. So now, Africa is going to collide into North America and South America. And we can see in 250 million years, Pangea is going to come back for one more sort of reunion party. That's pretty cool. You can see what the world will look like in a long time from now. I don't know how property taxes and people's houses and everything, you know, we'll of course adapt and evolve with it, but it just makes you think how different the world will be in 250 million years. I mean, that's a long time from now, so guys, don't get worried about your house. Credits for the diagrams of the play Tectonics goes to Timothy Kessler. Alright, we did it, guys. We finished. So good job, everyone. Please remember to subscribe. You can click on the top over here to subscribe to WasleyScience. And what I have for you is how it really happened, the Continental Drift. You may be familiar with this movie, I'm sure, you know, Ice Age. So go ahead and click on the video down here to watch how Continental Drift actually happened. Alright guys, thank you so much and take care.